So welcome to this lesson. This lesson will be on kinetic molecular theory of gases. So let's move into the study straight up. So kinetic molecular theory of gases is actually a theory that provides a microscopic evaluation or explanation for macroscopic particles of gases. So this theory is specifically for gases, and it explains gas behavior in terms of the motion of individual molecules and the forces between them. So this theory is critical for understanding gas laws and also the nature of gaseous substance. So from our previous lesson, we learned that gases are the kind of matter that they don't have definite shape, neither do they have definite shape, neither do they have definite volume. So moving on, this class will be talking basically on gases and the theory that actually govern the behavior of gases. This theory is known as the kinetic molecular theory of gases. So now let's head on. We said, according to this theory, it states that gas consists of large number of tiny particles in constant random motion. So this theory, as it is from its name, is you hear the word kinetics. So kinetics is actually talking about something that is in motion. So this theory is just trying to state that molecules of gases or particles of gases in a gaseous molecule, they are made up of large number of tiny particles that are in constant motion. They are in constant motion. So these particles are far apart relative to their sizes, and most of the volume of gases is empty space. So when you see maybe a gas, you see probably like a lighter, you would see, okay, this thing looks like as if it's liquid. But just give it space, like try opening it a bit, you see everything would escape immediately. So gas molecules, they would always want to stay far away from each other as much as possible, such that the volume you will see them occupy is actually almost like a virtual volume, because normally they would not want to stay within that confines. They would always want to spread as far as possible. That's why you see when you probably you are burning stuff, the gas that is going off from the combustion will be spreading as much as it can, as far as it can. So they are constantly in random motion, and also the molecules always want to move as far as possible from each other. This theory that states that gas molecules, they are in constant motion, is what is known as the kinetic molecular theory of gases. So collision between particles and the walls of a container are perfectly elastic, meaning that this collision, there is no energy loss. So when a gas molecule is probably contained in a container containing vessel, maybe your gas cylinder, when the particles of these gases strike the wall of the gas cylinder, they don't lose energy, neither do they gain energy. So what happens is that they just keep on repeating that same energy, meaning that as they are forced, the force that they use to strike the gas wall, the cylinder wall, is the same force they will bounce off with. They don't lose any of their energy because of collision. So that's part of the theory of this molecular theory of gases, that their motion, they have constant motion, and their collision is actually perfectly elastic, whether with themselves or with the walls of their containing vessel. So now, from this theory, it states that we know that pressure exerted by a gas arises from collision of the gas particles with the walls of its container. So when you hold a gas container and you shake it, when you shake that stuff, what you are feeling is not actually that the gas is liquid. What's happening is that the pressure that is exerted on this gas and the collision of this molecule is what we feel. The pressure that we feel, the pressure in the gas that we feel, is as a result of collision between the molecules of this gas with one another and the wall of the vessel. So that's the reason why when you see, if you shake gas container so much, when you shake them very well, what you're doing is you are creating more tension between these molecules. That's pressure. You are increasing their kinetic energy by shaking them. So that way you'll be causing there to be more pressure within that containing vessel. So from what I have here, I said the pressure exerted by a gas arises from collision of gas molecules with the walls of the container. So if you allow for more collision, the pressure would also increase. So the more frequently and forceful the collision, the higher the pressure, which I just said now. And temperature is a measure of the kinetic energy of gas particles. So we talked about pressure. So there are two parameters actually determine the level of kinetic energy in a gas container or in a gas between gas molecules. So these parameters are pressure, which I've explained earlier, and temperature. So temperature is actually the measure, it tells the measure of the average kinetic energy. So as temperature increases, so does the energy of gases increase as well as the speed. So I said if you increase pressure in gas molecule container, it would cause an increase in the speed of the molecule, or if you increase the pressure, it will increase the kinetic energy. Also, if you increase the temperature, the same would also happen. So now another postulate of this theory is that there are no attractive or repulsive force between gas particles. So this theorem, kinetic theory of gases, according to its theory, it states that they believe that gases don't have attractive force for one another at all, and they also don't have repulsive force for one another. So that they're trying to say that gases would not at any point want to hold themselves, neither would they at any point want to leave themselves. So that they just stay and they just exist as free particles, just moving, free particles that are in constant motion. So this assumption simplifies the mathematical treatment of gases and is valid for ideal gases under many conditions. So when you hear ideal actually means something that is not really true. It's just something that is ideal is just like an assumption of a perfect condition or a perfect state. So there is almost nothing that is perfect. So that's why you will hear some statement that say there is nothing that is like an ideal gas. There's no ideal gas that actually exists. So based on this idealization, they said gases, they don't have attractive force nor repulsive forces. And this actually is only true when gases are at low temperature and also low pressure. And also high temperature and low pressure. So when gases start having high pressure and also low temperature, they begin to deviate from the behavior that this kinetic molecular theory of gases explains. So the kinetic molecular theory is trying to state that gases are always in constant motion, and this constant motion is responsible for that gases are always in constant motion, and that these gases, they don't have attractive or repulsive force between one another. That's what the theory is trying to state. But this theory actually is true to some extent, but not true in all scenarios. That's why it's left as a theory, because it's true to some extent, but not completely true in all scenarios. So when gases are at low pressure and high temperature, they behave very well like ideal gases, and they will obey this kinetic theory. But when gases have high pressure or low temperature, they completely deviate from this molecular theory of gases. So the theory also explains that diffusion. It also tries to explain diffusion and effusion. So what is diffusion? Diffusion is the mixing of gases due to molecular motion. And in some other places you hear that is the movement of particles from a region of high concentration to a region of lower concentration, and so on. But in the case of gases, when you're talking about diffusion, you're trying to talk about how gases move from their initial position where they were highly concentrated to spread out to areas where they are not found, which are places where they have low concentration. So the same definition still applies here, but just in this case now, we're talking about gases mixing with their environment. That's, they don't stay at a spot, now moving out. That's how we define diffusion in terms of gases here in chemistry. And also effusion, on the other hand, is the passage of gases or gas particles through a tiny passage, through a tiny hole. So both phenomena support the idea that gas particles are in constant motion and exhibit random behavior. So the kinetic molecular theory was stating that gases are always in motion. So this phenomenon, that's diffusion and effusion, they try to explain this. They can be explained using this kinetic theory, because they can be proofs to the kinetic theory, because they believe also that gases are in constant motion, so they diffuse, and gases are in constant motion, so they undergo effusion. So with that being said, we're mentioning some of the limitations of the kinetic molecular theory. These limitations arise when you deal with real gases. So I was saying something about real gases at some slides ago. We talked about ideal gases, and I said ideal gases, they are not really real. They have this perfect behavior. That is, they have no attractive force, they have no repulsive force at the same time, they are in constant motion, they have no limitations, that kind of stuff. These are what ideal gases are. They seem very perfect, but in real life, we don't have ideal gases. Gases could behave to some extent like ideal gases, but they are not completely ideal, because when conditions change, they don't behave the same way throughout. But ideal gases, they are assumed to behave the same way throughout, regardless of temperature or pressure. But real gases, they have variations from this kinetic molecular theory. So now, the limitation of this kinetic molecular theory is that when you come to real gases now, real gases, they exhibit intermolecular force of attraction and occupy definite volume. They have a specific volume they can occupy. So the kinetic molecular theory was trying to say that gases, they don't have any force of attraction between themselves. But from real gas, from observation from real gas, it's found that real gas, there's a very tiny, though it's very, very tiny, but there are forces of attraction between particles of gases. So the modification of this theory, this kinetic molecular theory, was done by, well, who we know as van der Waals. So this van der Waals, he gave an equation that actually helps to correct the error or the limitations of this kinetic molecular theory. So when we go to the formulas for ideal gases and also real gases, we'll then see how van der Waals equation actually applied to help to modify and to validate also the kinetic molecular theory of gases. So with that being said, we'll be rounding up with this statement that the kinetic molecular theory offers a robust framework for interpretation of gas behavior, linking motion with observable phenomena such as pressure, temperature, and volume. It actually forms a theoretical basis for understanding and applying gas laws. So the kinetic molecular theory is very valid, but in some levels or some conditions, like what I said, under conditions of low temperature and high pressure, or high pressure, they behave differently. So this kinetic molecular theory deviates. So sometimes you might see it as kinetic molecular theory, but in some other cases you see it as KMT. So it's still the same thing. So this theory is very useful. Maybe I'll prefer using the word useful. It's very useful in understanding gases and also the behavior of gases. So that will be all for this lesson, and I'll say goodbye now.